Last week, we ended up discussing such an important property of quantum computing as quantum parallelism, and today we'll start a conversation about how this property can be used when performing quantum logical operations. We'll talk about quantum algorithms, and we'll see why the use of quantum algorithms for solving certain problems turns out to be more efficient than classical ones. Let's start with the problem formulated by David Deutsch and its decisive algorithm, which is in honor of the author, is called the Deutsch Algorithm. Suppose we have an unknown function f with a 1-bit range of values and a 1-bit definition domain. In other words, the argument of this function can be equal to either 0 or 1, and its values with this argument can also be equal to either 0 or 1. Such a function, which has only two values, is also called Boolean. If for two values of the argument the function f takes the same value, then such a function is called constant. If for each value of the argument of the function f takes different values, and f of 0 is not equal to f of 1, then the function f is called balanced. The Deutsch problem is to determine whether the function f is constant or balanced. Since we are dealing with a 1-bit function defined at a 1-bit definition domain, this problem can be reduced to calculating the sum of f of 0 and f of 1 modulo 2. It is easy to show. Let, for example, the function f be constant. Then, if f of 0 and f of 1 are both equals to 0, then the sum of the values of the function f will be equal to 0. And if f of 0 and f of 1 are both equals to 1, then the sum of the values of the function f will also be equal to 0, since we use the addition modulo 2, and 1 plus 1 modulo 2 is also 0. If the function f is balanced, then it is easy to show that the sum of its values modulo 2 will be equal to 1. Obviously, to solve such a problem with the help of classical calculations, we need at least two appeals to the computational circuit, which determines the value of the function f for a given value of the argument. Since the internal processes occurring in the circuit are left outside the framework of the problem, such a scheme is often called a black box or oracle. So, to determine whether the function f is constant or balanced, we need two references to the oracle. We need to know the value of f of 0 and the value of f of 1. Then, by comparing these values, we will be able to answer the question whether f is constant or balanced. If we use the quantum Deutsch algorithm, it turns out that all we need is just one appeal to the oracle, that is, to quantum computational scheme. The slide, which you see now, presents a calculation circuit that implements the Deutsch algorithm. This scheme consists of three Hadamard elements that make the transposition from the computational basis to the Hadamard basis. And also the third element UF performs the unitary transformation, which calculates the sum of the function f of x and f of y. It should be noted that the whole scheme is necessarily reversible, that is, by the qubit's output value we can find out which qubits were entered at its input. It will be convenient for us to introduce a timeline to gradually describe the operation of such a scheme. At the scheme, the most important points in time are indicated by dashed vertical lines. But here we have changed the notations, and instead of the time points T0, T1, and T1, we introduce the states of the qubits that correspond to these time points, that is, psi0, psi1, psi2, and psi3. So, at the circuit input, we have the qubit state of psi0. The first qubit in the state 0 will correspond to the argument or the data register, and the second qubit in the state 1 is the value of function f. Such values of the input bits are not accidental. Let's now consider the transformation from the state psi0 to the state psi1. So the state psi1 could be written as 0, 1, it's 2-qubit state, psi0, and after the Hadamard transformation of the first and the second qubit, we have the state 0 plus 1 divided by square root of 2 and 0 minus 1 divided by square root of 2. And we could write down this expression as following: 1 divided by square root of 2, the first qubit state 0, on the second qubit state 0 minus 1 divided by square root of 2, plus 1 divided by square root of 2, the first qubit state 1, multiplied by the second qubit state 0 minus 1 divided by square root of 2. For us, that form of the qubit state will be the most convenient. So, after the Hadamard transform over each bit of this input, we get the state psi1, which will be equal to an equiprobable superposition of the state 0 minus and the state 1 minus. Let's see how the oracle will act on such a state. Now, let's consider the transition from the state psi1 to the state psi2. But before we move on to the unitary oracle transformation, let's fix the target register at the state 1 divided by square root of 2, 0 minus 1, and analyze the result of the controlled U transformation performed on an arbitrary basis states of the control qubit X. So, for a unitary transformation U sub f on the control qubit X, we could write down the following: UF, the state X, 1 divided by square root of 2, 0 minus 1. And this is the control qubit, and this is the target qubit state. Let's rewrite it as following: UF X 0 minus UF X 1 divided by square root of 2. And by the definition of UF, this expression could be rewritten as X 0 plus f of X minus X 1 plus f of X divided by square root of 2, of course. And let's rewrite it in more convenient form. X 0 plus f of X minus 1 plus f of X divided by square root of 2. So, if the f of X equals to 0, then the target register is still unchanged. And if the f of X equals to 1, then the target register state changed as follows. So if f of x equals 1, then the state of the target register is minus 0 minus 1 over the square root of 2. This result could be written as uf x 0 minus 1 over the square root of 2 equals to x minus 1 in the power of f of x and 0 minus 1 divided by square root of 2. The phase factor minus 1 in the power of f of x could be associated not with the state of the target qubit, but with the state of the control qubit. So then the psi2 state could be finally written as psi2 equals to minus 1 f of 0 over the square root of 2 on the state 0, the state 0 minus 1 divided by square root of 2 plus minus 1 in the power of f of 1 divided by square root of 2 on the state 1 and as the state of the second qubit 0 minus 1 divided by square root of 2. So rewriting the psi2 state in more convenient form, we could write down the following. Psi2. It is minus 1 in the power of f of 0 of the state 0 plus minus 1 power of f of 1 on the state 1 divided by square root of 2. And the state of the target qubit, where for the sake of simplicity we write as just the Hadamard state minus. And if we take out the phase factor, we can write the following: minus 1 in the power of f of 0, state 0 plus minus 1 and the state f of 0 plus f of 1 on the state 1 divided by square root of 2 and on the Hadamard state minus. So here there is an arbitrary phase factor, so it could be just neglected in our further analysis. Thus, after the action of the oracle on the state psi1, we get the state psi2, in which the relative phase factor in the superposition of states 0 and 1 for the first qubit will contain information about the sum of the function value f of 0 and the value of the function f of 1. It is easy to see that if the function f is constant, that the sum of these values modulo 2 will give 0, and the state of the first qubit will be an equiprobable sum of states 0 and 1. If the function f is balanced, that the sum of the values of the function f modulo 2 will give 1, and the phase factor will become equal to minus 1, which means that the state of the first qubit will be an equiprobable difference of states 0 and 1. And in the last step, using the Hadamard element, we transform the first qubit from the Hadamard basis back to the computational basis. In the end, all we have to do is to measure the first qubit and the computational basis. If we get that the first qubit was in the state 0, then the function f is constant. And if we get that the first qubit was in state 1, then the function f is balanced. Thus, we obtained information on whether the function f is constant or balanced in just one call to the oracle. At the same time, we did not calculate the value of the function f itself for each value of the argument, as required by the classical algorithms. In the next lesson, we will look at the generalization of the Deutsch algorithm to the multidimensional case, that is, when the argument runs through neither 2, but 2 to the power of n of different values, where n is the natural number. That's all for now. Thanks for your attention.